In this PowerPoint, I'm going to introduce to you three new trigonometric functions called secant, cosecant, and cotangent, or you'll often see them abbreviated as sec, cosec, and cot. Now, before I introduce those, here's a quick starter for you to have a go at. I want you to think about whether you think these statements are true or false. So you could investigate them by putting in different values for x. So you could work out cos of different values, like, I don't know, 30 degrees maybe if you're in degree mode, cos of 30, and then cos of minus 30, and see if they turn out to be the same. Do the same thing with sine. You could work at sine of 30, and then sine of minus 30, see if you think they are the same. You don't have to do 30, try it for a couple of different x values. And then on the next slide, I'm going to discuss whether these are in fact true or false. Okay, so one of the statements in the starter was cos of x equals cos of minus x. Now, if we look at the graph, if I choose an x value, so for example, if I choose 30 degrees, and I go from 30 up to the cos graph and across, I don't know exactly what that y value is off the top of my head, but I can see roughly where it is on the y-axis. Now, if I then go to minus 30, and I go to the graph and across, I can see that it's actually the exact same y value. So cos of 30 and cos of minus 30 are exactly the same thing. So that statement was true. The other statement was the one with sine. I said sine of x equals sine of minus x. Let's try it with the sine graph. If I go to the number 30 in the sine graph, and I go up and across, I can see roughly where I am there on the y-axis. If I then go to minus 30, I go down and across, I can see I'm at a totally different place. Sine of 30 is a positive y-coordinate, and then sine of minus 30 is a negative y-coordinate. So that statement is false. Now actually, the y-coordinates, they would be very similar. They'd have the same numerical value, the same modulus, but one would be positive and one would be negative. So actually, if I wanted to make that correct, I'd have to say this. So sine of x and sine of minus x are not equal to each other. One is the negative of the other. So I could correct that initial statement like this. Okay, so let's now go on to the objectives for this PowerPoint. I'm going to introduce to you sec, cosec, and cot. I'm going to show you some trig identities with those in, and then we're going to start to solve some equations that have sec, cosec, and cot in them. So first of all, some definitions of what they are. These are definitions that you just need to memorize. Sec is the reciprocal of cos. So if you do 1 divided by cos of something, that is what sec is. That's the definition of sec. So sec of theta is the same as 1 over cos of theta. Cosec is 1 over sine, and cot is 1 over tan. So there's nothing yet to understand about these functions. I'm just defining to you exactly what they are. They're just the reciprocals of sine, cos, and tan. Here are the graphs, so you can see what they look like. So in the first picture, you can see the graph of sec of theta, y equals sec of theta. If I draw onto the graph, onto the same picture, I'll draw y equals cos of x. I think it's useful to see them together, because remember that sec is the reciprocal of cos. So if I draw the cos graph on, and we'll be able to compare the two. Oh, it's quite fiddly with this pen. So when we say reciprocal, we mean flip something upside down. Well, it does look a little bit like parts of the graph are flipped upside down. You can see that the sort of U shapes in the cos graph, they do appear to have flipped upside down. It's sort of like a reflection, it's almost like a mirror image, but those red lines would carry on going up forever towards infinity. they would never cross over the asymptotes. Okay, so on the next picture then, I'm going to draw the sine graph because cosec is the reciprocal of sine. So my graph's a little bit wiggly. So it's very similar, isn't it, to the sec graph? But those U-shapes and those upside down U-shapes are in slightly different positions. On the last graph, I'm just going to draw on the tan graph because tan is the reciprocal of cot, or cot is the reciprocal of tan. Just so you can see the graphs sort of next to each other. This time it's almost a reflection, isn't it? The curves seen backwards, and they've also moved slightly to the left or the right. Okay, so next thing then, we need to be able to work out sec, cosec and cot of different values. So if you have a look on your calculator to see if you can find the sec button, the cosec button or the cot button. I'm actually asking you a trick question here because most calculators don't have them. So if you have the Class Whiz calculator, you'll find that there's no cosec, cot or sec button on the calculator. So if you wanted to work one out, we're going to have to think of a different way. So say for example you wanted to work out cot of 120 in your calculator. I'm in degree mode now, by the way. I'm working in degrees, so I'm just going to change my calculator into degree mode. You can do cot, cosec and cot in degrees or radians, but obviously 120 is degrees. So if I wanted to work that out, I would have to know that cot is the reciprocal of tan. So as long as you remember that fact, then on your calculator you could type that in 1 over tan of 120 and you'd have your answer. So from the calculator it tells me that it's minus root 3 over 3. So here are some more examples from your booklet. To work out sec of 280, you'd have to know that sec is the reciprocal of cos. So on the calculator you could type it in as 1 over cos of 280. And then cot is the reciprocal of tan. So cot of 115 is 1 over tan of 115. It says that you can use the reciprocal key on the calculator. I don't tend to use that. I just tend to type in the fraction with a 1 on the top. So you could use the reciprocal button if you wanted to. So here are some examples from the booklet, page 17. I'm going to go through these handwritten solutions. So we're going to try and work out the exact value of sec of 210. We're going to try and do it without using a calculator. So first of all, I'm going to think about what I know about sec 210. Well, I know that sec is the reciprocal of cos. So if I can work out cos of 210, then I can just do its reciprocal and I'll know sec of 210. Now, one way to do this would be to do a cast diagram and to think about where 210 would be. So if I draw the cross to the cast diagram, so remember 0's there, 90, 180, 270, and then if we go all the way around full circle, we're back to 360. Now 210 is between 180 and 270, so on the picture I could mark 210 there. And now I could figure out that little angle in there must be 30 degrees, because the difference between 180 and 210 is 30. So now I know that each of these little angles is 30. So the first angle must have been 30 degrees. So I can now work out this little family of angles. So the one in the S quadrant will be 180 take away 30. And the one in the C quadrant will be 360 take away 30. Now I'm trying to work out cos of 210. So if I work out cos of 30, that's going to be really helpful. So in one of the previous PowerPoints I showed you a triangle that had a 30-degree angle in it. And it was the triangle that had sides 1, 2 and root 3. So using that triangle I can work out what cos of 30 is. Cos is adjacent over hypotenuse, so it's root 3 over 2. Now cos of 30 is a positive number. Looking at the cast diagram, the one that I want is cos of 210. And I can see that that is in the T quadrant. So only tan in that quadrant is positive. Cos would be a negative value. So I now know that cos is minus root 3 over 2. So now going back to my original question, I wanted to work out sec of 210. I knew that it was the reciprocal of cos of 210. So if I use my answer now and I just find the reciprocal of it, I'm going to get minus 2 over root 3. So there's my answer. You could make it even better by rationalising the denominator. So if we times the top and the bottom by root 3 over root 3, we get minus 2 root 3 over 3. So just rationalise the denominator, and that's a better answer. I'm going to go on to the next slide to do part B. So moving on to part B. Now part B is given in radians. I can spot that because it's written in terms of pi. So what I could do is change this now into degrees. So remember that pi is like 180 degrees. So if I do 3 times 180 divided by 4, I get 135. So I'm more confident working in degrees with a cast diagram, which is why I've changed that into degrees. So there's 0, there's 90, there's 180. So 135 must be in the S quadrant. So if I work out that little angle in there, the difference between 135 and 180, it's 45. So this angle must be 45 degrees. Now the question is asking me to find cosec of this. Cosec is the reciprocal of sine. So if I can figure out sine of 135, then I'll know cosec of 135. So let's see if we can figure out sine of 135. Well, from the cast diagram, I can see that if I work at sine of 45, that's going to be really helpful. And there's a triangle for that, which I showed you in a previous PowerPoint. Sine of 45 is opposite over hypotenuse, which is 1 over root 2. Now, sine of 45 is a positive value. Sine of 135 will also be a positive value, and it'll be exactly the same value. So I now know that sine of 135 is 1 over root 2. The question was, what is cosec of 135? Well, it's the reciprocal of that, which will be root 2. The question was in radians, but that doesn't matter because I've worked in degrees. Cosec of 3 pi over 4 is root 2. So next I'm going to move on to solving some equations. So we'll work through these two together. So in the first one, sec of x equals 1.56. Now if there was a sec button on the calculator, that would be great because then there'd also be an inverse sec button. So if I could do shift sec of 1.56, then I'd get my answer straight away. But unfortunately, there's no sec button, so I need to know that this is the reciprocal of cos. So if this is the reciprocal of cos, then cos of x must be the reciprocal of 1.56. So I've just done the reciprocal on both sides. So now, on the calculator, I could do inverse cos of 1 over 1.56 and get a value. So I'm in degree mode. Look at the question here. Here's the hint. So I'm going to do shift cos of 1 over 1.56. And it gives me an answer of about 50.1. I'm going to round there to 1 decimal place. So I've got one answer. To find the others, I can do a cast diagram. So I've got 50.1. Cos is a positive number, so I need the quadrants where cos is positive, so I need to figure this one out. So this is going to be 360 take away 50.1, which is 309.9. So my final answers are 50.1, 309.9. For this second example, first of all I would divide both sides by 3. So cot of x equals root 2 over 3. And then I would do the reciprocals. Now the reciprocal of cot is tan. So tan of x must equal 3 over root 2. So now on the calculator I can do shift tan 3 over root 2. Which is approximately 64.8. Then I can go to my cast diagram. I can mark off 64.8. Now this time it's tan that's positive, so I want the two quadrants where tan is positive. So I need to figure out this next one, so I'm going to do 180 plus 64.8, which is 244.8. So those are my two answers for x. Okay, so I'm going to move on now to some trigonometric identities. Last year you learned this one, which is really important. Sine squared plus cos squared always equals 1 for all values of theta. And we used that a lot last year in AS for solving equations. Now this year there are two new trig identities that you need to learn. They're not in the formula booklet, so you do have to memorise them. Sec squared theta equals 1 plus tan squared theta. And cosec squared theta equals 1 plus cot squared theta. So you need to memorise those two. On the next two slides now I'm going to go through the proof to prove to you where they come from. But remember you need to memorise these two. Okay, so I'm now going to prove this trig identity. One method for proof questions is to start from one of the sides and gradually try and turn it into the other side. So what I'll do is I'll start with the right hand side, which is 1 plus tan squared, and I'll try and gradually change it so that it becomes a sec squared. So first of all I'm going to fill in something that I know about tan. Well, I know that tan is the same as sine over cos, so tan squared is the same as sine squared over cos squared. And then the next step, well, if I want to add 1 onto a fraction, if you want to add fractions together, you want to try and make the denominators the same. So what I could do is, instead of writing 1, I could write that as cos squared over cos squared theta, because obviously that is the same as 1. And by writing it that way, it has the same denominator as the other fraction. So I can now add them together because they have that same denominator. So I can add the numerators, cos squared theta plus sine squared theta. Next, on the top there, you should recognise that cos squared plus sine squared always equals 1. So now it's 1 over cos squared theta. And by definition, 1 over cos is the same as sec, which means the 1 over cos squared is the same as sec squared. And that was the left-hand side from the trig identity. So it's fairly easy to prove. On the next slide, I'll just go through the other proof. Using the same idea, let's start with the right-hand side, which is 1 plus cot squared. And I'm going to gradually try and turn it into cosec squared. Now, I know that cot is the reciprocal of tan. So cot squared is the reciprocal of tan squared. Now remember that tan is sine over cos. The reciprocal of that is cos over sine. So tan squared is sine squared over cos squared. So if I flip that upside down to get its reciprocal, it becomes cos squared over sine squared. Next I could write 1 as sine squared theta over sine squared theta. And the reason I'm doing that is because now both of my fractions have the same denominator, so I can add the numerators. The top you should recognise, sine squared plus cos squared always equals 1. So we've got 1 over sine squared theta, and then by definition 1 over sine is cosec, so 1 over sine squared is cosec squared, and that was the left hand side that we were aiming for. You could be asked in an exam to do one of those proofs. That could come up, so it's worth writing those out a couple of times before an exam. So here is a proof question. It's quite a tricky one. What you'll find with proof questions is that the more you do, the better you'll get, because you'll pick up little tricks that can be used in them. A little trick on this one is a method of factorising called the difference between two squares. So for example, x squared minus a squared factorises into x plus a and x minus a. On the left hand side of this question, this is the difference between cosec squared theta squared and cot squared theta squared, because the power of 4 is like squaring something and then squaring it again. So this will factorise into cosec squared theta plus cot squared theta, and then cosec squared theta minus cot squared theta. Okay, the next step that we could do is we could use one of our trig identities from earlier. So earlier on we learned that cosec squared is the same as 1 plus cot squared, or rearranged, cosec squared minus cot squared is equal to 1. So that bracket there is just 1. So we can ignore that bracket and we can just have the first bracket, which is cosec squared theta plus cot squared theta. Next we could put in something that we know about cosec and cot. Cosec is the reciprocal of sine, so this is 1 over sine squared, and cot is the reciprocal of tan. Tan is sine over cos, so if I do the reciprocal, cos squared over sine squared, these have the same denominator, so I can add them together. And then finally on the bottom, we can replace sine squared with 1 minus cos squared, because remember we learned in AS sine squared plus cos squared always equals 1. So if we rearrange that, sine squared is the same as 1 minus cos squared. So this was the left hand side that we were aiming for. So that was definitely quite a tricky proof question. Little trick to try and remember. The difference between two squares is a great way to factorise something like this one. Now the next thing that we need to be able to do is to use those trig identities to solve equations. So the trig identity that we're going to use in this question is that sec squared theta is equal to 1 plus tan squared theta. We're looking for all the values of theta in the range 0 to 360. Now looking at this equation, there's a mixture of sec squared and tan. We don't want to have the mixture. I'd rather them all to be the same. So what we can do here is we can replace the sec squared theta with 1 plus tan squared theta, and then leave all the rest as it was. So plus 5 equals 5 tan theta. So now it's become a quadratic in tan of theta. So I'm going to get everything onto one side, put the 1 and the 5 together, plus 6. And now we solve that quadratic using our normal method. So sometimes it factorises, sometimes you can use the quadratic formula. This one will factorise. And I find that the quickest method if it works. So I'm looking for two numbers that times together to make 6. They've got to add up to minus 5. So the numbers that I'm looking for there are minus 3 and minus 2. So either tan theta equals 3 or tan theta equals 2. So on the calculator, making sure I'm in degree mode, I'm going to do shift tan of 3, which is about 71.6 if I round it, and shift tan of 2, which is about 63.4. I can then do my cast diagrams to find out any other possible values. So if I do the 71.6 first, so I'll put that in the A quadrant. On this one, tan of theta was 3, so tan is positive, so those are the two quadrants that I want. So I've got to fill in the T quadrant by doing 180 add 71.6, which would be 251.6, so I'll add that onto my list. The other one we've got is 63.4. Again, tan is a positive number, so it's the same two quadrants. I've got to do 180 add 63.4, which is 243.4. So I've ended up with 4 possible answers.